All right, so before we get to the second fundamental theorem of calculus, I want to quickly review with a warm-up problem here. Going to review the things that we covered right before we left for break. So we have this function 2 secant squared of x. And we have the interval from negative pi over 4 to pi over 4. And we want to find the average value of the function. So does anyone remember how we would find the average value?
1 over b minus a times the integral of f of x d of x.
Okay, good. We would multiply this integral that you see here by 1 over b minus a. Remember, we can't just take the average of the middle of the interval and say that that's going to be our mean, because we don't know where exactly the middle is going to be vertically, okay? But this is going to help us find the middle vertically. 1 over b minus a times the integral from negative pi over 4 to pi over 4 of 2 secant squared of x dx. Okay? So, first of all, and here we're doing part A. We'll call this first part A. All right? So let's walk our way through this. What's b in this case? Pi over 4. What's a? Negative pi over 4. So we're doing that times. Now, what is the integral of 2 secant squared?
2 tangent. Or just
2 tangent. Do you guys agree with that?
no.
Is the integral of secant squared tangent?
The derivative.
Well, let's think. The derivative of tangent is
Secant squared.
secant squared. So yeah, the integral of secant squared is tangent. So yeah, we're right. So we're going to take this, but we need to use our fundamental theorem of calculus and evaluate this from negative pi over 4 to pi over 4. Okay? So now we're simplifying a little bit. As I simplify this, pi over 4 plus pi over 4 is going to be 2 pi over 4, which is pi over 2. So I have 1 over pi over 2, which of course will be 2 over pi. And then I need to multiply that by 2 tangent of pi over 4 minus 2 tangent of negative pi over 4. Now, from your knowledge of the unit circle, what is tangent of pi over 4?
1.
It's 1, okay? It's 1. So we have 2 times 1 minus 2 times, what's tangent of negative pi over 4?
Negative. Just 1.
It's the same thing.
Negative.
Is it 1 or negative 1?
Probably 1.
All students take calculus, so if negative pi over 4 is in which quadrant?
It's negative.
It's in the fourth quadrant, so this is negative 1. Okay?
What is that?
This is a way of remembering what trig functions are positive in the different quadrants. So angles, all of the trig functions are positive in the first quadrant. If you have a second quadrant angle, only the sine and cosecant, because it's a reciprocal, are positive. In the third quadrant, tangent is positive. And in the fourth quadrant, cosine is positive. Okay? That's a little way of remembering it. All students take calculus. It's a little way. So. All right. It won't go away. Anyways. So we keep simplifying here, and we get 2 over pi times 4, so that is 8 over pi. Okay? So that is the average value of 2 secant squared of x.
What does it mean exactly by the average value?
If you were able to evaluate the function for every possible x between a and b, and you averaged that infinite number of values together, you would get 8 over pi.
It's just the mean, right?
It's the mean. Average value. Mean value. Okay? And that's why this is called the mean value theorem, because the mean value theorem says that this is the mean value, and there will always be at least one value of x, and we use the variable c to represent that. There will always be some c where f of c equals that 1 over b minus a times the integral from a to b of f of x dx.
So is that like if you were doing the triangle, not the triangle, sorry, the rectangles with the sum, is it like the average area of each interval?
No, it's not the average area, it's actually the average y coordinate.
Oh, okay. Okay.
Okay, so we already figured out what that whole integral on the right equals. It equals 8 over pi. What is f of c? Well, my function is 2 secant squared x. So this is 2 secant squared of c. And we got to solve for c. Okay? So that means secant squared of c is going to be 4 over pi. I can flip both sides. And then what's the reciprocal of secant?
So the cosine.
Cosine. So cosine squared of c equals pi over 4. And at this point, we would take the square root. Okay, so cosine of c is the square root of pi over 2, and that's plus or minus. However, think about the interval. The interval we're dealing with is from negative pi over 4 to pi over 4. And this is cosine. So what quadrants am I dealing with if I'm going negative pi over 4 to pi over 4?
1 and 4.
I'm in the 1 and 4. Cosine is positive in both of those, right? So I actually don't need the negative square root of pi over 2. Okay? So I'll now take the inverse cosine of both sides, making sure the calculator's in radians, because this isn't our unit circle, of course. But we can then figure out what the value is.
0.632.
0.632. Okay. And that is in the first quadrant. We would also want to give it in the fourth quadrant. So we could actually do positive or negative 0.632.
Mr. How come we don't do plus or minus square root of pi over 2 again?
Because the minus one will put us in the second and third quadrants. So we don't need where cosine is negative. But we do need both the first quadrant and the fourth quadrant answer here. Is this correct?
Wait, I got 0.48.
0.48?
You find the inverse cosine of that.
Yeah, we do the inverse cosine. Oh, you hit cosine? Okay. So now AP wants at least 3 decimal places, so it's 0.4,
1.
2.
Oh, 2, yeah.
.482 if you round?
Yeah.
Okay. When in doubt, just give more decimal places, okay? At least give 3. Alright, so that's a little bit of a warm-up, kind of a reminder, hopefully, of what we did before you left. If it was after you left, some of you need to go back and review, maybe come by for some extra help. We can go over that with you. Okay, so just to sum up what exactly we found, okay? There's this value, and again, I don't know exactly what this function looks like, but just for example's sake, let's say this is 0.482, this is a negative 0.482. These points both have a y coordinate of 8 over pi.
Oh.
And those are both the average value within this interval from negative pi over 4 to pi over 4. Okay? So right here, that's the average value of all of the y's in that interval. Okay, so based on my drawing's probably not really accurate, but you guys will get the idea there. Okay? So this 8 over pi, that was the f of c that we then used over right here. Okay? That whole integral thing is right here. That's 8 over pi, and that equals f of c. Okay? Okay, so let's take a look at and develop our second fundamental theorem of calculus. Alright, so basically what we have is this, okay? There are actually two things that we can do with a definite integral, okay? One is just what we've been doing with the first fundamental theorem of calculus, and that is where a and b are both constants, and we simply plug in values for those constants. We do capital F of b minus capital F of a and get the value of the integral. However, we can also use definite integrals to change the variable that we're using. Watch this. Here, we have a function of t, and we're taking the integral of f of t dt, okay? However, notice we're taking the integral from the constant a to the variable f, or x. And our antiderivative that we're going to find is going to be a function of x. Okay? Now, that may not make a whole lot of sense, but let me show you an example of this. And I think it will make a little better sense, okay? So here we have the integral from 0 to x of cosine of t dt. Let's just take this very straightforward way. Okay, what's the integral of cosine of t dt? Sine of t. Okay? So, sine of t, but according to the fundamental theorem of calculus, I need to evaluate that from 0 to x. Okay? Is everyone with me so far? Alright? So, that means I have sine of x minus sine of 0. Well, what's sine of 0? 0. So that's simply sine of x. Okay? Now, if, I'm not going to do all of these, but let's say, for example, I did the integral from 0 to 0 of cosine of t dt. What's the integral from 0 to 0 of anything? 0. If a and b are equal, your area is 0. right? That was one of our properties. Okay? Well, let's say we did pi over 6. Okay? Well, that would be sine of t evaluated from pi over 6 to 0. Well, what is sine of pi over 6? Come on, we know our unit circle.
1/2.
A half minus 0 is just 1/2. Well, guess what? That's the same thing as sine of pi over 6. We saw already that if we, rather than doing each of these different integrals over and over and over again, we can do the integral once in terms of x, and then we could just plug in pi over 6, pi over 4, pi over 3, pi over 2. And we'd get the 1/2, root 2 over 2, root 3 over 2, and 1. Okay? So, that's kind of the opening idea of what we're doing here. So basically what you can see here is you need to think of the antiderivative as accumulating the area under the curve. Okay? It's an accumulation, all right? The result is the original integrand, with only the variable changed. Notice here, the derivative of the antiderivative. In this case, the antiderivative was sine of x. What's the derivative of sine of x? It's cosine of x. Well, we just showed if we took the derivative of the integral we just found, the integral we just found was sine. What's the derivative of sine? Cosine of x. Okay? So basically, it's again kind of using that inverse relationship of the derivative and the integral, okay? And that is what we then summarize here with the second fundamental theorem of calculus, all right? And this is what this is saying. If f is continuous on an open interval I containing a, so that lower bound has to be on an interval where this is continuous, then for every x in the interval, the derivative of the integral from a to x of f of t dt is simply going to equal f of x. Okay? So notice the derivative of the integral is f of x. Okay?
When you say a needs to be, it needs to be a constant, right? But it could have, is there ever going to be a time where a or b equals like cosine of something? And would that be considered a constant because the graph isn't?
If it's cosine of like pi over 2, sure. So you could just plug in the value.
Yeah.
If it were like cosine of x, that's you're getting into some things that are beyond the scope of this class. You can do that, but that's a little beyond where we're headed.
So the graph of a needs, the graph of what needs to be continuous? The function needs to be?
The function, yeah. And basically what we're doing here is we're changing variables. We're changing from representing it in terms of time to representing it in terms of x. Okay?
So if the function isn't continuous, but a is a constant, you can't use the second one.
That's correct. Yeah. It'd have to be continuous on the interval that you're looking at. Yeah.
What does changing a do? Like as long as it meets the conditions?
Yeah, as long as it, and we'll actually see this in a sec, I'll show you. It actually doesn't matter what you put in for a, as long as it's continuous on that interval and the a is something on that interval.
Okay.
Okay? Now, just to show us here, if we know the antiderivative, capital F of x, okay, is the integral from -1 to x of the square root of t squared plus 1 dt, then notice here this says f prime of x equals what?
Square root of t squared plus 1 dt.
No. F prime of x
T,
It's the same as.
2t plus t half.
it's f prime of x, right? So it should have x's in it.
So is it square root of x squared plus 1?
That's right. It's just the square root of x squared plus 1. You take the integrand
So we just need to replace t.
and replace t with x. Okay? So integrating it, notice this square root function is continuous where t is -1. Okay, it is defined there, it's continuous there. Okay? So f prime of x is the square root of x squared minus 1, or plus 1. And again, that goes back here. That goes back here to different notation. The derivative of the antiderivative is the original function, right?
Yeah.
Okay. Well, the antiderivative was this whole integral. If I take the derivative of that whole integral, I get the original function, which is the square root of x squared plus 1. Okay? Now, this is where I think we'll see why that number at the bottom, as long as it's on the interval, doesn't matter. Okay? We're actually going to do this one both ways. First of all, let's use what we just learned to find f prime of x. Okay? So, part A, f prime of x, if f of x is the integral from 4 to x of square root of t dt, what is f prime of x?
Square root of x.
Square root of x. Alright? That's nice and simple. Okay? B, let's do it the long way. We're going to actually do the integration and then take the derivative to find f prime of x. Okay? So f of x is the integral. What's the integral of square root of t dt?
2/3 t to the third t.
Yeah, it's 2/3 t to the 3/2, right? You add 1 to the exponent and divide by the new exponent. Alright? A little rusty on these? Okay? It'll come back. We're going to evaluate that from 4 to x. Okay? So notice we have 2/3 t to the 3/2 minus 2/3 times 4 to the 3/2. Okay?
Why wouldn't that be x?
Oh, yeah, sorry. Thank you. X. I forgot to plug it in. X to the 3/2 minus 2/3 times 4 to the 3/2. Okay? Now, as long as we recognize it's a constant, it really doesn't matter, but we'll simplify anyways. What's 4 to the 3/2 power? What's the square root of 4?
16. 2.
Square root of 4 is 2. Cubed is
8.
8. Alright, so 3/2 power of 4 is the square root cubed, which is 8. So 8 times 2/3 is 16/3. Okay? So that is f of x. That's what we just found. So now we need to take the derivative of that. Well, we get 3/2 times 2/3 x to the 1/2 power minus 0. That is why it doesn't matter what number we pick as the beginning of our interval, as long as it's continuous on the interval. I could have picked x equals 2. I could have picked it to go from 1 to x, or 5 to x, or 20 to x. It doesn't matter as long as it's continuous, okay? Because every time when I take this derivative, that's going to be a constant, and the derivative is going to be 0, okay? So now when I do that, notice the 3/2 and 2/3 cancel out, and I get f prime of x is the square root of x. Same thing we got back here. Okay? Alright, so that's just a little kind of proof, if you will, that it works either way. Now, can you do it the second way? Sure. It works. But the idea of the second fundamental theorem of calculus is that you don't have to. Okay? All right. One more here. Doing the same thing. If I use the second fundamental theorem of calculus, f prime of x is what?
Secant cubed times tangent.
Secant what?
Cubed to the third.
No, it's just you can't have tangent.
Yeah, it's just secant x times tangent x. Okay?
But isn't tangent? Wait.
You don't have to do any actual derivatives or integrals.
Oh, we just. I thought we were. Never mind.
Yeah.
I thought isn't Are we doing the derivative?
For this, well, yeah, we're doing the derivative, but we're doing the derivative using the fundamental theorem of calculus, the second part. So we can simply replace the t's with the x's here. Okay? Now, if we were to do this the longer way, what's the integral of secant t tangent t? It's secant, yeah. Okay? So that's secant of t evaluated from pi over 3 to x. Okay? Well, that is secant x minus secant of pi over 3. That's f of x. So when I go to take the derivative of that, what's the derivative of secant?
Tangent times secant.
Yeah, tangent times secant, or secant times tangent. What's the derivative of secant of pi over 3?
Pi over 3.
Huh?
It's a secant of 3 times, pi over 3 times 8.
What's the derivative of secant of pi over 3?
Product.
What is secant of pi over 3?
It's 1 over cosine pi.
Which is a number, right?
2.
2.
What's the derivative of a constant?
0.
0. Remember, this is a constant. When I take the derivative, it's gone. Okay? So I get secant x tangent x. Same thing I got here. Okay?
Wait, so it's just one of the two ways?
Those are two ways of doing the same thing. One's obviously a little bit faster.
Yeah. Yeah.
Okay?
Wouldn't that be just like so much quicker?
All right, now, let's look at one quick use of this and then that'll be it. All right? So, we want to find capital F as a function of x. Here we have it written as an integral. Okay? And we can do it one of two ways. All right? we can do it kind of the longer way that we were just looking at, where we actually take the integral from 2 to x of negative 2t to the negative third power. And what's the integral of negative 2t to the negative third?
Negative 2t to the third over
T to the negative
T to the negative 2. It's going to be negative 2t to the negative 2 over negative 2. Those negative 2's cancel out. So we have just t to the negative 2 power evaluated from 2 to x. So that's going to be 1 over x squared minus 1 over 2 squared. That is capital F of x. Okay.
What did the negative 2 win?
If you add 1, remember you're adding 1 to the exponent and dividing by the new
Dividing
exponent,
by one.
so it cancels.
Yeah.
Okay? Now I can plug in 2 and 5 and 8, and I can find those values. You guys can do that part, okay? The alternative would actually be using what we just did, but notice that would only give you f prime of x would be a negative 2 over x cubed. And then I would need to take the integral of that. But notice at that point, essentially we're doing the same thing. We have an x now. Alright? The problem there is though that we have a indefinite integral. Okay? So we would have trouble knowing where to go at that point. So in this case, this second method is going to be simpler. Okay? All right.